my name is Vojislav Đukić and I'll tell you about Project Iris. Project Iris is a multi-year effort at Microsoft Research Cambridge that explores novel designs of regional cloud networks. The project is motivated by rapid growth of cloud network traffic across data centers. Project Iris is a part of a bigger Optics for the Cloud team at Microsoft Research Cambridge, which explores disruptive technologies across the entire cloud stack. At the beginning of cloud era, data centers were built in remote areas that had cheap power connectivity and sufficiently large piece of land to accommodate mega data centers with tens of thousands of machines. However, finding such large plots of land in regions like Europe or the Far East is challenging. Moreover, there is an increasing desire to minimize latency to customers by placing data centers close to large urban regions, which amplifies the problem of finding land for mega data centers. Today, cloud providers take a different approach. Instead of building one mega data center per cloud region, they split it into multiple smaller facilities spread around the area and interconnect them with a dedicated high bandwidth network called Data Center Interconnect or DCI. The map shows how the geography of such a region with 4 data centers might look like in the metropolitan area of London. Each major cloud provider operates tens of regions around the globe, with each region consisting of multiple smaller data centers connected by DCI. The impact of a shift to regional architecture is evident in the number of deployed 100G DWDM ports over time, where growth has been exponential year over year. It is important to note that the total number of ports deployed in DCI is 2 orders of magnitude higher compared to the number of ports in wide area networks. This makes Data Center Interconnect one of the most important pieces of the cloud puzzle. So then, how do we interconnect a few data centers within tens of kilometers from each other? Using the available fiber in the region, we can interconnect data centers in various ways, starting from a centralized topology with only one switching point for the entire region, over semi-distributed with several switching points, to fully distributed designs where each data center is directly connected to every other data center in the region. We perform a detailed analysis of today's design space across a number of dimensions based on data from Azure regions and testbed experiments. As I will show, DCI design involves complex trade-off across a number of metrics. Certain solutions reduce latency at the same time increase deployment flexibility, which is essential in urban areas. Although they look like an ideal design points, they have a serious problem. The cost of these solutions is so high that they become practically infeasible. Because of these insights, we propose a new all-optical DCI architecture that has positive impact on the cost across the entire design space and practically unlocks previously expensive solutions. Let's now look at DCI problem in more detail. We start with the inputs to the design process. First, we need a map of available fiber in the area. Here you can see a map of dark fiber in London operated by only one fiber provider, where each blue line represents a fiber duct. Metro areas are often full of low-cost fiber. A single fiber duct commonly has hundreds of fibers that can be used for building data center interconnects. Second, we need the location and the number of data centers. Typically, each region has less than 20 data centers. Also, it is important to know the capacity that must be supported by the network. Data center number, location, and capacity are determined using a variety of business objectives, which are outside of the scope of this work since we don't control them. Finally, we need the location of so-called fiber huts. These are very small facilities that are cross points of fiber cables and can be used to host switching equipment. Throughout this talk, I'll use the simple example which has 4 data centers marked in red. Blue lines represent fiber ducts, while brown points are fiber huts. Using the inputs above, we want to design a network that achieves a certain set of goals and operational constraints. First, we want to provide a latency SLA. To assure that the latency between a pair of data centers will not exceed a certain threshold, we have to bound the maximum distance between data centers. In the agreement with DCI practices, we bound distance to 120 kilometers. Also, a pair of data centers should communicate over the shortest path available. This requirement is motivated by minimizing application latency. Second, data center interconnect needs to be able to satisfy any traffic pattern that does not violate per DC capacity. Regional data centers should be able to satisfy the same traffic characteristics as if they were in a single mega data center. And third, we want to satisfy previous two requirements under a set of failure scenarios. As a running example, we consider up to 2 edge failures in the network topology, which is aligned with today's industry practices. Now, since we know what are our goals, let's talk about the design process itself. What does it mean to design a data center interconnect? First, we need to decide which fiber ducts to use and how much capacity in terms of number of fibers to reserve in each one of them. And second, we need to decide which fiber huts we want to use to place network equipment for switching and routing. Let's first examine a candidate DCI architecture which uses a centralized hub. All data centers connect to the hub and all DCI traffic goes through the hub. Designing and provisioning a hub is a well-understood problem in networking. In practice, though, 2 hubs are necessary for redundancy. Although simple, this centralized architecture has several problems. First, it can cause a latency inflation. We demonstrate that on a real topology with 2 data centers and 2 hubs. 2 data centers are at the top, while 2 hubs are at the bottom. Black lines represent available fiber ducts in the region. When data centers want to communicate, they have to go through the hub. Note that although there is a direct short link between them, the centralized architecture does not exploit that link. This limitation increases latency by 6 times. In our analysis, we show that in at least 20% of cases we consider, we observe at least 2x latency inflation caused by a centralized design. Another problem is that centralized approach limits the data center placement flexibility. Due to latency constraint, each data center must be within a certain distance r from a hub, as we show here. Since the latency SLA must hold even under failures, each data center must be placed within distance r from both hubs. This means that the real service area where we can place data centers is within the intersection of these 2 circles. Placing hubs closer to each other increases service area, but may also cause latency inflation as we demonstrated previously. Also, hubs close to each other have higher probability of failing together. This exposes an interesting trade-off in centralized topologies. We have to pick between reliability and latency on one side and service area and sitting flexibility on the other. Another approach to building DCI would be to use direct links between each pair of data centers. Although expensive and complex, this approach has certain benefits. First, the latency between each pair of data centers is optimal because a pair of data centers is always able to use the shortest path possible. When it comes to the size of service area, distributed topology allows greater flexibility. Here we show an example of service area for 6 data centers marked in yellow and 2 hubs marked in blue in London for a centralized topology. Service area is a result of intersection of 2 circles around 2 hubs. If we remove the hubs and make the topology distributed, the service area increases significantly. This happens because data centers are now not limited by the hubs with small radius of 60 kilometers, but rather each data center can talk to any other data centers within the radius of 120 kilometers. This is not an isolated case. We calculate service area for centralized and distributed topology across many real cloud regions and show that distributed approach can bring up to 5 times more area compared to a centralized approach, which provides a huge advantage in planning cloud regions in densely populated cities. Although distributed approach has substantial benefits in terms of latency and the size of service area, it increases the complexity of the network. Let me illustrate that using an example. Here we have a centralized topology where each data center requires P ports to connect to the hub. If a new data center is added, only that data center and the hub must be changed, while other data centers remain untouched. However, in a distributed topology, each data center now requires 3 times the ports. More generally, for a region with n data centers, the region can be implemented with order of n square ports, while centralized topology requires only order of n ports. This directly translates to more management complexity and higher cost. Also, if a data center is added to the topology, there are many places in the network that require changes in capacity provisioning. Comparing just the port cost for a region with 16 data centers, a distributed approach is 7 times more expensive compared to a centralized topology due to a substantial difference in total number of ports they are required. Looking at the entire design space, by moving from a centralized to a distributed topology, the latency and system flexibility improve, but at the same time the cost increases drastically. Additionally, as we move toward more distributed topologies, the complexity of the network increases as there are many more components to be managed. From the operational perspective, centralized topology has the most desired properties. It is simple to manage and extend. Practically, the increase in cost and complexity restrict design choices that cloud providers have today toward more centralized approaches. This motivated us to propose ARIS, a new all-optical data center interconnect architecture that reduces both cost and complexity and unlocks the entire design space for practical purposes. So how does ARIS work? To understand how ARIS reduces cost and complexity, we first have to take a look at the main inefficiency of today's DCI deployments, number of ports and transceivers they require. Since the traffic is switched electrically, typically in today's DCI, every time a fiber arrives at a switching point, it must be terminated by 40 transceivers and ports, one per color. Also, leaving the switching point requires another 40 transceivers. This quickly inflates the cost, especially in a distributed topology. In our example, if each data center operates only a single fiber, we would need to deploy a total of 320 expensive in-network transceivers as well as ports. Instead of frequent signal conversion and electrical switching, ARIS relies on switching the traffic entirely in the optical domain, which would reduce the total number of components necessary since there are no in-network transceivers. In this particular example, ARIS requires only 8 optical ports instead of 320 and no in-network transceivers. To understand what the transition from electrical to optical switching practically means, let me start by taking a more detailed look at today's DCI links. Multiple transceivers at DCI 1 are combined into a single fiber and sent to a switching point, where the traffic is converted back to electrical signal, switched, and then again converted to the optical domain, where it's finally forwarded to the destination. As the optical signal travels through fiber and other optical components, it loses power. So we need 2 amplifiers per point-to-point link, one amplifier to compensate the loss caused by packing multiple colors into a single fiber, and another amplifier to compensate the power loss caused by a long-distance fiber. Now ideally, we would like to replace only electrical switching part with optical without touching other components in the system. Unfortunately, this is not possible. Optical switching introduces additional challenges that must be considered. These challenges need to be solved taking into account the specification of DCI transceivers and other physical layer components. In this context, the signal should arrive at the receiver with sufficient signal power. Also, signal needs sufficiently high optical signal-to-noise ratio. And third, optical control plane can become quite complex, so we want to simplify it by minimizing the number of devices that require reconfiguration. First, optical amplifiers introduce noise to the signal. More amplifiers means more noise. The signal can be decoded only with sufficiently high optical signal-to-noise ratio or OSNR. As we experimentally show in the paper, without signal regeneration, OSNR budget allows us to safely use only one in-network amplifier. Besides worrying about signal quality, we have to guarantee that the signal arrives at the receiver with sufficient amount of power. This is why we have to carefully place the one in-network amplifier. In the paper, we provide an algorithm for amplifier placement that guarantees meeting all optical constraints. When it comes to switching technology, we can take 2 approaches. Wavelength switching, that allows us to switch at the level of each individual wavelength, and coarse-grained fiber switching that can move only the entire fiber. Although wavelength switching provides finer switching granularity, we can only have one wavelength switching point end-to-end due to OSNR and power constraints. This limited form of wavelength switching introduces substantial complexity and brings marginal cost savings, as we show in the paper. This is why ARIS relies completely on simple fiber switching technology. However, fiber switching does not come for free. It actually requires additional network capacity. Consider a traditional link with electrical packet switching that goes from data center 1 and carries C fibers worth of traffic to any other destination in the region. In the paper, we show that if we would like to implement an equivalent link using fiber switching, we would need C plus n-1 physical fibers to guarantee non-blocking network, where n is number of destinations. This results in order of n squared additional fibers for a distributed topology. Although not perfect, we are ready to take this overhead because regional fiber is cheap relative to transceivers, and the total number of destinations is commonly less than 20. Also note that the fiber overhead does not require laying new fiber ducts in the metro area. Existing fiber ducts usually carry hundreds of fibers, with many of them being currently unused. The third challenge we have to consider in the optical domain is what happens to a system when reconfiguration is necessary due to changes in traffic demand. We illustrate the major problems on the simple topology with 3 data centers. Initially, data center 1 sends only 2 wavelengths, red and green, to data center 2. Assume that the traffic demand changes. There is no traffic between data center 1 and data center 2, but there are 2 new wavelengths, green and blue, coming from data center 3. First, the receiver at data center 2 will notice much lower signal power due to longer distance that new signal traverses. And second, the output of the amplifier in the middle depends on the colors it amplifies. A different set of colors can lead to a completely different amplification result. Dealing with optical amplification of a signal that varies in power and the colors it carries has been a serious challenge in optics community with no easy solution. This is why we decided to avoid online adjustment of power levels by first introducing power limiters in front of amplifiers that prevent changes in the signal power due to changes in distance the signal traverses. Second, we introduce noise sources. They partially fill fiber with wavelengths that are missing, so that optical amplifiers always see the same set of colors. Noise sources together with fiber switching and power limiters guarantee that no online adjustments of power level is necessary even under traffic changes. We implemented a full physical layer architecture in, so to say, region in a rack, using all components of a DCI architecture including transceivers, amplifiers, tens of kilometers of fiber, as well as wavelength and fiber switching equipment. This resulted in a small-scale region with 3 data centers that we assembled at Microsoft Research Cambridge. Iris architecture does not require active management of power levels, significantly lowering the bar for deployment, and our analysis on the real equipment shows that this is feasible with truly minimal performance impact. Since we showed that ARIS can be practically implemented, I would like to quantify its benefits compared to traditional electrical links. 2 identical topologies, one implemented using electrical links and another using ARIS, by design satisfy operational constraints in terms of non-blocking switching, resilience, and latency performance. However, the overall cost of these 2 systems is very different. We tested the cost across 10 real fiber maps and different placement of data centers in a distributed topology, and using real cloud provider component prices amortized over time. We showed that ARIS reduces the cost by 4 to 12 times compared to electrical switching. Also, we evaluate the complexity of 2 approaches in terms of total number of in-network ports and showed that ARIS reduces complexity by an order of magnitude. Before I conclude my talk, I would like to highlight several interesting pieces of our work that I omitted due to time constraint, but you can find them in the paper. Detailed analysis of latency and service area in regional networks based on real cloud regions, algorithms for capacity provisioning under failures and amplifier placement that minimizes the overall cost, large-scale simulations and analysis of dynamic network behavior and reconfiguration, many physical layer experiments, and finally, we provide a whole new design and analysis of an architecture that combines wavelength switching with ARIS to minimize the fiber overhead that ARIS has. Though that to truly unlock benefits of the whole design space, we had to jointly solve a wide spectrum of problems across technologies and network layers. These include challenges like topology designed to meet SLAs, capacity to provide non-blocking connectivity, and resilience to ensure that SLAs are preserved even under failures. All that has been done while respecting many physical layer limitations, as we previously discussed. This all resulted in ARIS, a novel all-optical DCI architecture that unlocks the advantages of distributed topologies while lowering the cost and complexity. It provides benefits across the entire design space. ARIS was possible thanks to multidisciplinary optics for the cloud team at Microsoft Research Cambridge and insights across the entire cloud stack. Thank you all for watching.